Additive color mixing, basis of any color television system is additive color mixing. Light from two or more colors obtained from independent source or through filter can create a combined sensation of different color. Means if red and green are mixed, you will see yellow, if red and blue are mixed, you will see magenta. This is the representation. Here we have the blue, red, green. If red and green are mixed, then they form yellow, red and blue are mixed, they form magenta. If blue and green are formed mixed, they form cyan, and if all of them are mixed, means green, blue and red in a specific proportion, then we form a color which is called white, means it contains all the colors blue, red and green. So, these colors basically are called primary colors. These three colors are called primary colors. All other colors are formed with the mixing of these three primary colors. Subtractive mixing, use reflecting property of pigment used in painting and color print. What we see in practical life is all subtractive mixing. What we see is reflection, how the reflection comes whenever the total light, means white light, means visible spectrum falls on a particular surface. Some of the or entire or all of the wavelengths except a particular wavelength are absorbed, that is they are subtracted from the total visible spectrum, and whatever is not absorbed is reflected, is seen as a color of that surface. So, in this way this theory of subtractive mixing is the theory which we use in practical life, daily life. Now, I will discuss Grassmann's law. According to this law, eye is not able to distinguish each of the color that mix to form a new color, but instead perceive only the resultant color. I behave as the output of three cones are additive, means whatever the color we see, it is not able to distinguish that in what proportion the colors are mixed. What we observe is the resultant of the mixing of the three colors. The brightness impression created by the combined light source is numerically equal to the sum of brightness of three primary colors that constitutes the single light. Not only the resultant color is formed by the combination of three primary colors, or it depends upon the proportion in which three primary colors are mixed, which gives result to a new color, the resultant color, but at the same time the brightness of that particular color is also algebraic sum of the brightnesses of three primary colors individually. What is the brightness level of individual brightness level of any particular primary color is numerically added when a new color is formed with the help of mixing of two or more primary colors. So, when two or more primary colors are mixed, in what proportion they have been mixed will result in the formation of the resultant color, but at the same time the brightness of the resultant color will also be equal to the numerical sum of the brightnesses of the three primary colors individually taken. So, this is Grassmann's law. Now, we will discuss the color characteristics, what the colors characteristics are. Any color has three characteristics to specify its visual information. These are luminance, hue and saturation. Amount of light intensity as perceived by eye regardless of color of object is luminance. Different color has different brightness response. Dark red appear black, yellow appear white, blue appears gray. So, this is luminance, or we can call it the corresponding brightness. If it is dark and you are if it is say dark red and you are watching it on your monochrome TV, it will appear as black. If it is yellow, it will appear as white, and if it is blue it will appear as gray. So, this is luminance of particular color. Color contains brightness also. So, this is explained with these examples. Next is hue. This is very important. Predominated spectral color of received light. Whatever the light we receive, what is predominant in that? That spectral color which is predominating is hue of that color. Color of object is distinguished by its hue. Any color is distinguished by its hue. Appearance, tint, we also call it tint. Different hues result from different wavelengths of spectral radiation. Where the hue comes from? It comes from the wavelength of spectral radiation. Hues are perceived as such by the sets of cones in the retina. There are 3 cones in the retina, and they are placed in the form of a triangle, that is the set. Their combined result is the color whatever we see, and what the hue is, it is also the resultant of the combination of those 3 cones. This is spectral purity of color light. How pure the light is? This spectral purity of that light. Since single hue colors occur very rarely, this indicates the amount of other color present. This is saturation what we are talking about. A fully saturated color has no white. If a color is fully saturated, it will not have any white. Means it is pure color. Saturation means purity. How much purity is there? How pure a color is? If it is fully saturated, it means there is no white. Or in other way, we should also say that how little it is being affected by the presence of white. We also define it like this: how little it is being affected by the presence of white. And if there is no white, it means it is fully saturated. It is fully saturated, it means it is 0 affected. So, it means it is fully saturated, it means it has no white. Vivid green is fully saturated color. When diluted by white, it becomes light green. If you have pure green, then it is fully saturated, but if we mix white to it, it becomes light green. So, this is an example what the saturation is. If it is mixed with white, it becomes light green, it means it is not fully saturated. If we take out white from it and we are left with only green, dark green, pure green, vivid green, then we call it is fully saturated color, means it is affected, it is 0 affected by the presence of white, or it is not affected by the presence of white, or there is no white color present at all in this. So, that is fully saturated color. This is spectral purity of color. We already have discussed it. Repeat. Chromaticity diagram. Chromaticity diagram is a convenient space coordinate representation of all spectral colors and their mixtures based on tri-stimulus values of primary colors contained by them. Tri-stimulus means because they give response to the cones. So, it is called tri-stimulus. We will just see the picture, it is also in the form of a triangle almost. It is a 2-dimensional representation. Here is the chromaticity diagram. It is a 2-dimensional representation. Here we see the white, it is pink, red, yellow, green. We have all the colors and they are shown on a 2-dimensional plane. In chromaticity diagram, red, green and blue have been standardized as wavelengths of 700, 646.1 and 438.8 nanometers respectively. X and Y denote color coordinates. For example, white lies at x is equal to 0.31 and y at 0.32. 0.31 and 0.32, here lies the white. This is 3D representation. How a particular color has got its brightness. Chromaticity diagram we just have seen. This is the chromaticity diagram in 2 dimension. This is in 3 dimension. In 3 dimension means if it is black, we will see it very deep. If it is gray, we will see it somewhat above that, and if it is purely white, it will just appear as if it is coming out of the picture. So, that is white. This represents the 3. This picture shows the 3 dimensional representation of luminance or brightness. Whenever we increase the brightness, it appears as if the picture is somewhat out of that. So, it is come as if it is coming out of this, as you can see from this. So, white means pure bright. This is chromaticity diagram. There we had where a particular color is, suppose here is green, here is white, and here is red. So, these 3 colors, if we see in that colored chromaticity diagram, here is green, here is white, and here is pure red. So, in this way these colors mix into each other to form new colors, and we see the chromaticity diagram in its real color representation or its color output. Gamma correction, this is very important. Color difference signal R minus y or B minus y, G minus y can be regenerated from these 2 color difference signals R minus y and B y minus y at receiver. Color video signal contain 2 independent information. What those informations are? One is hue and second is saturation. For compatibility of monochrome with color, it is necessary to add color signal into standard TV channel that is fully occupied with Y signal. It is possible because of frequency interleaving. Now, we will see color TV camera. I already have explained color TV camera. Here is the source, here are the 3 color filters. They allow only red, green and blue to pass through, and then we have pre-video amplifiers for red, green and blue. They are independent amplifiers. They work irrespective of the presence of other amplifiers, and here is that combining matrix, and we have the output. Now, we will discuss the color display tubes. The color television picture tube screen is coated with 3 different phosphors, one for each of chosen red, green and blue primaries. The 3 phosphors are physically separate from one another, and each is energized by an electron beam of intensity that is proportional to the respective color voltage reproduced in television receiver. Means whatever the voltage is present there, that particular voltage of a particular color will strike with the spot of a particular phosphor. Means for green electron gun, we have a green spot of phosphorus. For red we have red, and for yellow for say blue we have blue. So, every electron beam will strike its own phosphorus, corresponding phosphorus spot, and then the colors are produced there. The object is to produce 3 coincident raster with which produce the red, green and blue contents of the transmitted picture. While seeing from normal viewing distance, the eye integrates the 3 color information to convey the sensation of a hue at each part of the picture. What we see is the resultant of combination of those 3 spots, because those 3 spots are very closely spaced, they are placed very close to each other. So, the human eye cannot differentiate between the 2 spots. We can't tell that which spot is where. What we see is combination of those 3 spots. What is at the red, what is proportion at the red, what is proportion at the green, and what is proportion at the blue. What we see is a hue which is combined combination, the resultant combination of the combined brightnesses of those 3 phosphorus spots. Based on the gun configuration and the manner in which phosphors are arranged on the screen, 3 different types of color picture tubes have been developed. These are delta gun tube, gun inline or precision inline tube, and third type is Trintron or single sun tube. Here is the delta gun tube. In delta gun tube we have red, green and blue. These are the three tube neck. If we see this tube neck, we have red, green and blue 3 electron guns. They are placed at 120 degree apart. So, they are placed here, and then we have a shadow mask which is shown here. This is shadow mask, and here is the color phosphor screen. So, the phosphorus which is deposited on the screen is also of this form, green, blue and red, and as you can see from here, the electron beam emerging out of green will strike with green only, coming out of red will strike with red only, and coming out of blue will strike with blue only, and before striking here they are made to pass through a shadow mask which allows the focusing and which ensures that a particular electron beam strikes with the particular phosphorus for which it is meant. So, this is one type of tube. Because these three spots are arranged like this at 120 degree apart. So, they form a triangle, or it is also called delta. That is why the name given to this color picture tube is delta color picture tube. Though it ensures the color display, but it has got some drawbacks. What those drawbacks are, we will quickly have a look at them. Convergence is difficult and involves considerable circuit complexity and service adjustments. In most delta gun tubes, 4 static convergence magnets and a dynamic convergence assembly are employed. The focus cannot be sharp over the entire screen because the focus and convergence planes cannot remain coincident for the 3 beams which emanate from guns positioned at 120 degree with respect to each other around the tube axis. So, this is a difficult task to deflect them in the same proportion because they are placed 120 degree apart. Next is the electron transparency of mask is very low, since it intercepts over 80% of the beam currents, because we have seen that shadow mask. So, the light will pass through only the hole which is meant for the focusing. So, 80% of the light is intercepted by that mask. So, 80% efficiency is reduced due to the presence of that type of mask. So, to overcome these limitations or drawbacks, the next type of tube which was formed was precision inline or PIL color picture tube. Here the difference is that these 3 electron guns are placed in a line, that is why I call 3 inline guns, it has been given name, and as they are placed in line. So, the B, G and R means blue, green and red phosphors are not coated in the form of dots as in the case of delta gun. Here they are coated in the form of strips. Blue, green and red strips are coated on the screen, and the corresponding electron beam strike the red, green and blue phosphorus, which gives us the resultant combination of the resultant color. So, this is difference. Similarly, the shadow mask is also different. So, with the help of this the convergence problem is avoided to a certain extent. At the same time, as the shadow mask is of this type, so that 80% signal strength which was lost in the shadow mask is also reduced considerably with the help of this type of picture tube. The third type of picture tube is Trintron. We will discuss sometime next time whenever we come. So, for here I come to end of this chapter. Thank you.